Now question 4 AI and II says, what is the structure of graphite and diamond? So yeah, these two are both allotropes of carbon. We'll be looking at the structure. So let's see. So now the structure of graphite is a giant hexagonal layered macromolecular structure. What does hexagonal mean? It means that it has 6 sides of interlocking micromolecular structure, while diamond has a giant, this one is three-dimensional rigid tetrahedral network. So now use the exact WAEC phrasing. Remember, hexagonal layered is for graphite and 3D rigid tetrahedral is for diamond. AIII, explain briefly why diamond is hard and a non-conductor of electricity, while graphite is soft and an electrical conductor. So now remember to always mention delocalized or free mobile electrons for graphite conductivity and sliding layers for its softness. So for diamond, each carbon is covalently bonded to four others in a rigid network with NO, that means no mobile electrons. So it is covalently bonded to four others in a rigid, so there are no free mobile electrons in between. So therefore it becomes a hard and non-conductor type of carbon. While graphite, each carbon is bonded to three three others in layers. The layers can slide over each other, so they are soft, and then the fourth valence electron is then delocalized and free, or you can say mobile, allowing it to conduct. Bi, state what is achieved at each of the following stages in the purification of town water. So this is water treatment, aeration, screening, sedimentation. So let's look at that. Now, aeration involves to expose water to oxygen to dissolve ion 2 to insoluble ion 3 compounds or remove bad odors. Now, aeration isn't just about adding oxygen, so they also wanted to mention the oxidation of soluble ion 2 to insoluble ion 3 compounds. So it can also be used to remove bad odors. While screening is to remove large solid floating impurities. So these are the ones that float, so they will remove them like twigs or leaves. And sedimentation is to allow heavy suspended particles called floc to settle at the bottom. So once it's settled, they can now collect the top liquid. Just think about it like when you pour sand into a bottle and shake, or you dissolve this thing. If you not like, yes, some sands, and you shake, after some time you keep it out, it will dissolve back down. BII, name two substances responsible for hardness in water. Now any of these two will earn the marks. Now remember to use IUPAC name. So now here, number one, calcium ions. Yeah, you can pick any out of these four for to answer. So calcium ions or magnesium ions. And then next one we have calcium tetraozosulfate 6, CaSO4. And we have magnesium tetraoxosulfate 6MgSO4, or you can say calcium hydrogen trioxocarbonate 4. So those are these. So now these 2 and 3 are what causes permanent hardness, while the last one, 4, is what causes temporary hardness. It can also be magnesium here instead of calcium, magnesium hydrogen trioxocarbonate 4. So let's move on to the next one. BIII. State 2 methods for the removal of hardness in water. So we're going to state just 2. Now we have here boiling. So now boiling removes temporary hardness only. We have second one, addition of washing soda Na2CO3, and we have the use of ion exchange resins, also known as the permute process, and number 4, distillation. So now washing soda and permute are the most reliable answers because they remove both temporary and permanent hardness. So those ones can be used for both temporary and hardness, so that's why it is more preferred. Now for BIV, give one disadvantage of hard water. Now these are, you can pick any one. Now number 1, it wastes soap by forming scum. Now it wastes soap, you see that scum on the water, that is how it wastes soap. And then 2, it causes foreign or scaling in kettles and industry. So now this scaling is like a this white or gray crusty layer. So that's what this foreign or scaling. So this is due to the accumulation of the insoluble carbonates from calcium and magnesium in temporal hardness. So that can also occur in pipes too. Now let's move to the next one. Tip: industrial boiler scaling is highly dangerous. It can lead to boiler explosions. Now for CI, describe briefly the extraction of tin from its ore. So now here we have the tin ore. Now the ore is known as the cassiterite and the tin oxide SnO2, and it's concentrated by washing and roasted to remove impurities. So now number 2, it is then mixed with coke, which is a carbon, and heated strongly in a reverberatory furnace where it is then reduced to molten tin. So oxygen is given off. So the key extraction method of metals moderately low in the reactivity series tin, and this is reduction with carbon, while those above is electrolysis. Don't forget. Now let's move. Write a balanced chemical equation for the reaction, which is the extraction of tin we talked about earlier. So now these are the reaction. So we have tin oxide SnO2 solid plus carbon, 2 moles of carbon solid will give us tin molten in liquid form plus 2 moles of carbon monoxide gas. Or alternatively, this is another acceptable equation, so we just reduce the moles. So it's still the same SnO2 solid or plus carbon solid, which will give us tin liquid molten form plus CO2. but this one, instead of carbon monoxide, we have CO2, carbon dioxide. So here carbon acts as a reducing agent in the furnace, stripping the oxygen away from the tin 4 oxide. Write an equation for the reaction of tin with oxygen and chlorine. So here we have, for reaction with oxygen, SN tin plus O2 gas would give us SnO2 solid. Now this is that ore, remember, so it will give us tin dioxide. And then for reaction with chlorine, we have tin solid plus 2 moles of chlorine gas will react to give us tin tetrachloride, or you can call it stannic chloride, but remember we're dealing with IUPAC nomenclature. So that tin tetrachloride is liquid. Let's move on to the next one. Okay, now in our next video we'll be looking at industrial acids and metals, question 5. So that is all for this video. Remember to go to the next one and view it.